Alright, the next scheduling approach we will talk about is shortest job first. This again, you can infer from the name, the shortest job or the job which requires the smallest amount of time is executed first. So we ended first come first served by saying if a shorter job comes in later than a longer job, it will have to spend that entire duration waiting, right? So just to overcome that problem, we have here this example this scheduling algorithm where the shortest jobs are taken first. So again we will look at an example, we'll draw the Gantt chart, we'll compute the waiting time and turnaround time. And again I want to mention this caveat here. We are going by the assumption that all of these processes arrived more or less at the same time instant of 0. They arrived in this order, of course, but that we assume all of them arrived at the same time of 0. There could be examples where you have a specific arrival time and the arrival time could be 1, 2, 3, 4 and or whatever, in which case whichever time instance you are looking at, you will only consider the processes which have arrived by then. So for example, I'll take a minute to explain that example quickly and then we'll come back to this. So supposing you had arrival times and P1 arrived at 1, P2 arrived at 2, time 2, P3 arrived at 3 and P4 arrived at 4. Arrival time meaning the time it enters into the ready queue. Then let us say I am at time instance 3 and I am looking for a process to fill my Gantt chart. I can only take one from the processes P1, P2, P3 because P4 has not yet arrived. It will arrive only at time instance 4. So I cannot schedule P4 here. So I have to schedule either P1 or P2 or P3, or if for some reason all of them have been executed or something like that, if there is no process which I can schedule, then from 3 to 4 my CPU will remain idle. So this is also a possible situation which can arise. I just wanted to mention that caveat so that if you are faced with such kind of numericals, you're not confused. So with that out of the way, let's get back to shortest job first scheduling. As the name suggests, the job with the shortest time duration is taken first. Again, this is non-preemptive scheduling. So once you pick a job, you finish it and then you go for the next job. So here we have an example, 4 jobs P1, 2, 3, 4 with burst time 6, 8, 7 and 3 respectively. We assume all of them arrived at the same time instance of 0 in this sequence. Now, as in any scheduling algorithm, first step, draw the Gantt chart. The shortest job here is P4. So we first pick P4 and we use up 3 units of time for that. Now P4 is done. You have 3 options, 6, 8 and 7. 6 being the shortest, you will take P1. P1 goes on for the next 6 units of time. P1 also done. Now you have P2 with 8 units and P3 with 7 units. 7 being the smaller number, you will take P3, 9 plus 7, 16. So for the next 7 units, P3 runs. That's also done. So you have only one process left. So for the next 8 units, P2 it is. So that is your Gantt chart. Now the waiting time for P4, it would be 0 milliseconds. For P1, it would be 3 milliseconds. For P3, it would be 9 milliseconds from 0 to 9, and for P2 it would be 16 milliseconds. Similarly, the turnaround time for P4, it entered the queue at 0 and its execution completed at 3. So turnaround time for P4 would be 3 milliseconds. For P1, it would be 9 because it entered at 0 and completed at 9. For P3, it would be 16. And for P2, it would be 24. So now that this data is available, you can calculate the average wait time and the average turnaround time. So this is definitely going to be much better than your first come first served, in the sense that it will minimize your wait time and all. But the problem is you will not always have a list of processes like this in your CPU, right? As in, here the entire list was given to us beforehand, so at every step we pick the minimum. But in a system, in real time, that is not how things work. You're doing a bunch of processes and then suddenly something comes in between. So things keep popping up all the time. And you don't know how many processes are going to come the next instant, how many of them are going to be long, how many of them are going to be short, how long, how short. You have no idea about all this. So if you are going to try to find the minimum in the ready queue, By the time you search the ready queue and find the shortest task, another 10 tasks would have been added to the end of the ready queue. So if you keep searching, you might probably not be able to find the minimum at all, because processes keep getting added at that speed to your ready queue. So definitely this is more efficient than FCFS in terms of reducing your wait time and all, but practically this is not very easy to implement. So that is the disadvantage of this technique.